Good evening, everybody, and welcome to this IDEA Community Talk. Tonight, it's Xiao,
Yes.
who's going to be talking about his current work, really fascinating work on basically point processing. And this, just a reminder that this presentation is being recorded. Please feel free to ask questions, but just keep in mind that it is being recorded. And with that, Shou, you can just switch over to just share your, and we should see it pop up.
Screen, right? Sure. Is that right?
We should see yours come up.
Right.
Beautiful. And then why don't you go full? All right, take it away.
Thank you, John. So my name is Xiao. I'm a fifth-year PhD student here at the RPI. I'm affiliated with the mathematical sciences department and also trying to get my master's degree in computer science. And then thank you, everyone, for coming. So today I'm going to talk about learning and inference from temporal event sequences. This is my talk outline. First, I'm going to introduce point process, and then from the second bullet point to the fourth, we'll be talking about a couple of problems that involve in point process, the learning and inference problems, and then I'll conclude with today's talk. So let me okay. All right. So point process actually has a lot of applications in real life. You can think of here on the left side, there's earthquakes. Earthquakes happen in sort of in continuous time. Earthquakes are discrete event. At some point, there's an event, and then suddenly there's another event, right? There's an earthquake, and you can also see EHR, a patient visits, you see a doctor, and then at one point, and then another point, going to take some medicine. So these are the EHR records, and you have also social networks when people tweet, right? Tweet at some time point, and then at another point they tweet again. So and also DeFi, decentralized finance, these are for like transactional data. So at one point, people trade, perform some action on the Bitcoin. Okay, and then another point and perform another action. And same with the e-commerce, shopping, online shopping. So they are associated with a timestamp and also a label. And insurance claims, there's an accident at some point, and then there's a one type of claim arrival. So yeah, these are real applications for point process. And to be specific, we're interested in temporal and point processes. So we have an event sequence, which is the time of the event. This is the simplest. If we only have one type of event, the univariate case, there's only a time associated with that event. And then we can look at the one way to characterize is looking at the conditional intensity function, which is this lambda term condition on the past history. This is essentially saying, I can't point at, but the E is the expectation term. So within a very small amount of time, we can see the event increases by 1 in this case. So n is the number of the event at t. So this is conditional intensity functions really describe the rate of event happening at a point of time given the history. And we can also think of this as this term as a probability of event happening in that small interval. But prior to that, from the history after t, there's no event happening. And usually, like I mentioned in a lot of applications, they are with marks or labels. That means each event time are associated with the label. So R is the time, yi is a label associated with that time. And sometimes you also get to see that lambda E, which means that you can consider the event type E happening at some rate on the timeline. Here, there's an example. We have 3 different event types. They are arriving on the timeline, right? So yeah, in this case, this is actually a Hawkes process, which are you can visualize that how event E0, once event E0 excites the other type of events, right? Whenever E0 happens, then the rate of E1, E2 increase, so they will happen with more frequently. So yeah, there are a lot of examples for conditional intensity function. The simplest one is the homogeneous Poisson process, which is characterized by the rate being constant. It doesn't change with the time, right? So it's just a random way. So whatever happened, the event comes at the rate maybe maybe one accident per month, right? You can see, but when with the actual realization, when it happened during a month, it varies, right? But we know the rate is 1. And then in homogeneous Poisson is really that the rate happens as a function of time. And as I mentioned, the Hawkes process is one of the very important stochastic process here. It's also called self-exciting because of the conditional intensity happens through an additive effect, linear additive effect, meaning that if one event happened, then it may triggers another event to happen. So in the 1D case, it'll trigger itself, right? If one event happens, then more likely another event will happen, and then eventually it dies down, right? So, and then D-dimensional is you have many cases, you have many types that one type will trigger another. You can think of maybe in social network, if you have there's different tweeting event. If you tweeted something maybe with a hot topic, and then someone else will tweet again, so there will be clustering effect, right? You can think of this, and you also hear the words neurotemporal point process. Essentially, that to model this function with a neural network, right? Instead of you have a parametric form, now you have a neural network to model that function. Excuse me. So, but this function is non-negative, or it's always positive, right? The rate is always positive. So when you're actually doing some neural net models with that, you have to be careful.
So just on the inhomogeneous Poisson, is that just one example?
Yes, one
That's just
example.
Okay, I was going to say, it's kind of, yeah.
Yeah. I should have be more specific. This is just an example, but the conditional intensity is a function of time. So.
Okay, got it.
Yeah, sorry, there's no more math.
Yeah, but there's pictures too. So.
Excuse me. So there are a few key quantities that are very interesting and they are related, right? So F is the probability density. So that means at this point, what's the probability density for the next event to arrive? And then F, the capital F is its cumulative probability. Now, S is the survival probability, meaning that it's 1 minus F. So the probability that nothing happened up to that point. And then this is lambda P is the conditional intensity. So the key takeaway, and this is maybe looks very complicated, but the key takeaway is the four. Once you obtain one, then you can sort of derive the other, right? So that actually these mini models of point process with neural networks, you can directly model this F. And some people model the cumulative, right? When the neural network designed to model that cumulative version. So yeah, and then usually once you do trying to learn the parameter, a good way is to maximize the log likelihood to get the parameter. So yeah, this is, you don't have to remember this complicated version, but one thing to remember actually is there's an integral involved, right? Integral, because that means when you actually do trying to calculate, there's probably involved some sort of a numerical estimation, because the integral, if your lambda does not, that integral does not have a closed form, analytical form, then you have to do it numerically. And sometimes people, with the multivariate case, people will make a simplified version by decoupling the time and label term. Okay, I hope I do not confuse, but the takeaway is with the integral term, right? And you can acquire, the one of the four terms and convert to another, right, when you do the modeling. Sure, there are other ways to set your objective other than maximize the log likelihood, such as you can do adversarial training, you can do reinforcement learning type of model to do something like that. Yeah, and there are many applications or problems in this domain. That is prediction. Prediction, sure, is very important, right? So you can look at, given the history, what's the next event to come, right, to arrive? Or you can ask the long term, within maybe in 10 months or 10 years, what's the next event? What will be happening, right? So long range. There's also structural inference that you can do. That is, so for one type of event, you're trying to learn the parent of that event. Why do we learn the parent? Because graph is a high-level abstraction, right? That provides a visual representation of your data and how they interaction. Excuse me. Rather than you have to deal with a sequence of complex events. You can abstract with a high-level graph. You can see how they interact, right? This is a very helpful visual representation. So a parent and their states, you can learn. You can do for structural inference, and then causal inference is you're trying to quantify the effect or quantify the inference, right? So if you intervene on the system, or you perform some action, you want to know that if I perform on maybe type A and on C, right? You want to see how maybe the rate of arrival or C occurring will decrease. And you want to quantify how much that decrease is, right? For example, during the last couple of years, President Trump gives out the relief fund, right? Now, you might be interested to see if that a couple times, right? You might be interested in how that relief fund will do to protest rate in each of the cities, happening in society, right? There are other problems such as probabilistic queries. That is, what's the probability for A to happen before B or or vice versa, right? And change point detection. At some point, the dynamic changes, right? You want to see if there's a shift. And anomaly detection, that may be related to computer security. So if you have some sort of actions, maybe in the system log, right? Then you can sort of detect, is this an event or this sequence of event, a subsequence of event, are they really a computer attack or not, right? So, okay, so let's look at the first problem, the learning problem. So the Hawkes process, classic Hawkes process are not flexible enough to maybe to capture complex dependency. And then maybe you don't have enough data to train a neural network for a point process model, right? You may very small amount of data. And maybe you have to numerical estimate that term, right? The integral term. So these are the sort of the problems. Now, what I propose, inspired by sort of transfer learning and large language models, I'm sure you guys heard of, right? So they are, what these models usually do is do pre-training and fine-tuning, right? So pre-training is essentially the process of you train with a lot of data that's not your target data, right? So you train with other set of data or learning from different books. Now you can extract, you can extract very good high-level representation, and then you can use this representation on your target data for very good performances, right? Usually they're cheap. So similarly here, we also propose a new self-supervised learning paradigm for homogeneous transfer. And we designed a novel pre-training strategy by masking not only the events, random event instances, the epochs are just instances, fancy word for, and we also insert void event, which I'll show in the next slides. And we do with combine position and temporal encoding, and we apply a lower triangular attention so that this pretty much covers, so only future events can look at past event instead of large language models do when they look at the contextual event, right, from both sides. And we show that there will be up to 15% increase in terms of prediction accuracy. This is pretty amazing, right? We compare with the absolute, the state of art transformer point process models, right? And we can still achieve this 15%. So yeah, this is what this model is about. So here on the left-hand side, the green is the pre-training step. So pre-training, we have an event sequence A, right? We have event sequence here A. And now the orange ones, okay. So the orange color shapes, right, are the event. But with the solid one, with the solid arrows are what was the original event sequence. And then we insert, right, between two event sequences, we insert the void sequence that to tell the model, hey, there's no events happening here. And then we label this as null event. So we introduce a new event, right? And then we mask it with this grayish color. So these are randomly selected event to mask, right? And then we use it. This is the transformer model to predict on these events. I don't know. Does that make sense? Sort of.
So go ahead.
Yes.
So what are these events coming from? Because you mentioned limited.
Yeah. Oh, yeah. The event sequence, we have a sequence. Suppose we have a sequence, right? The sequence will happen. The sequence is what we have, A, right? So these are our source data. That means S is target data. The source data can be from multiple streams, maybe. You can think of if you are, let's say if you are trying to your target data is some electronic commerce data shopping, maybe for cosmetic product, right? Then my source data can be from other electronic records, right? Yeah, electronic transactions, but they could be for electronic products, right? So we just train on the electronic products that we don't touch a cosmetic product, for example. Right, so in the pre-training, we have the original sequence will be the A sequence, but without the data point with dash arrows.
So the dash here, excuse me,
Is sampled.
those are planted nulls.
Right.
There
Planted
definitely is
yeah,
nothing
insert,
there.
yeah.
And then the gray are where there was an event, but your
For my pre-training task,
Right,
yeah. So I can sample, I insert, right? For between every two events, I insert, a plant event, right? And then I do random sample to cover or mask. And these will be sent to the model to predict in my pre-training process. Yeah. Yes, once I pre-train my model, I know all of the parameters I learn the parameters from my transformer network, right? And then I can send my target sequence, right? Send my target sequence, then I will get H hat there. These are my learned representation for this new sequence, right? The target sequence. And then what I have to do is just to do fine tuning. That means I just train with a small neural network for next label prediction, next time prediction. Yeah, these are the core idea. I think I just briefly explained. That is, I sample void event and then insert these events. And then I mask randomly like 15% for all of the instances, and then train by minimize the label prediction loss, which is the softmax, and the time prediction loss, which I use the mean square error for prediction. Yeah, and then I fine tune on the actual target data, again, minimize with the two losses. One is time prediction, and then second is label prediction. And here are some synthetic experiments that I did. One is through simulate Hawk's point process data. You can see the conditional intensity for the Hawk's process with exponential kernel is there's, whenever there's an event, this intensity gets jumped, right? There's a jump, right? This is the self-exciting property. And then the proximal graphical event model is characterized by the sort of piecewise constant, right? Piecewise constant conditional intensity, which means whenever the parental configuration changes its state, the conditional intensity changes. So you can see that I compare with a couple of state-of-art transformer-based baseline. The T stands for transformer. So IMTPP, ERPP, TLNM, and transformer hogs. And then our model event former. So we want to have the smaller for time prediction, we use RMSE. So that means the smaller the better, and type is accuracy. So the larger the better. So I highlight this event. So overall, the take home message is consistent improvement by 1% to 3% here on the synthetic experiment. And then on the real benchmarks, there will be, so we use six sets of data, three sets of data, so two as a couple. So we have the DeFi data, so we pre-train on the polygon network and then apply on the mainnet, and then pre-train on cosmetic and apply and fine-tune on the electronic. And then this is political conflict data from India to Bangladesh. So you can see that overall, there's about 15% of reduction for error in time prediction. And then, 12% for prediction accuracy overall. And then even if you pre-train for the baseline, if they train with both sets of data, the source and target, you can still see that our model is performed the best here. Yeah, this is a quite significant improvement up to 15%. Yes?
So I wanted to clarify. So the other baseline models, they are pre-trained using the same data that is used to pre-train your model?
Right, I combine yes, that's right. So I combine the source and target data for the model to do the.
So they always see the same data? Those are not, you're not using like pre-trained, like state-of-art, like models, weight, I guess?
So without the plots, right? Without the plot, so I have a source data and the target data, right? Source data I only for my event former, right? I can use. That's for the first table out here, right? And then the baseline, they only train on the target data, right? So you have train, delve, and test data. So they will get train and validate on the delve data and then test on the test subset. Now the second set of experiment with the plot sign is now they get access to the source data as well and train. So does that make sense?
I think so.
Well, I think the root of the question is you're not cheating.
No.
That's right. I'm not cheating. So
If it's working better than like, say, it's like Google's pre-trained weights, that's like amazing. But I wasn't sure if the setup was like.
oh, so yeah, you were thinking of the pre-trained weights are, I think they are mainly for language models, right?
Yeah.
You have the timestamp. So they will not necessarily fit into that category. I cannot just use their pre-trained weight, right?
Oh, I see. I've just seen like people using like that for other tasks like transfer learning. So I was wondering if that was the case.
Right. These are sort of, point process a little different, because you see the time, or time is important when that arrives, right? Because if you have a shorter period of time, maybe in the electronic e-commerce data, maybe they just click on it, view it, right? And then if you're larger time, they might put into a cart and buy it, right? So there's information about time. So yeah, the now we come to the third part. So structural inference. I put a quotation mark here because here is slightly different, but yeah, it's got similar flavor. So Identifying the influencing set is very important. For example, in physics, you have different particles interact with each other, but you know, what you observe is you have your observed dynamics, right, happening for that particles, but there's unobserved graph that governs how they interact with each other. And then in machine learning and knowledge discovery, you can also see there are the latent graph discovery that will govern event dynamics, event interaction. In past research, a main approach is using message passing algorithm, but I think it's not very efficient because of RNN type of update. So we use attention and transformer for more efficient ways because of parallelization computing.
Don't worry about it. Because Windows. Right.
And yeah, and the transformer type also captures potential long-range dependencies. So yeah, here's the overview of our proposed model. That's decoder type of model, right? So there's a latent graph that we can capture. So I'll briefly talk about here, but then we'll look into that in next slide. So what I call is inference-aware attention for multivariate temporal point processes. So it's good for identifying inferences for event type of interest through the attention mechanism. And the encoder is really models the pairwise interaction. And then decoder learns a dynamic model given an inferencing set. So the key of this is to learn a probabilistic distribution as a latent distribution, right? As I showed in the earlier slides, yeah. Now, let the A to be a binary random matrix so that Eij is the probability of event J inference I. So if we have different, three different event type A, B, C, right? So you assume that maybe 70% of probability C will inference A, and then maybe 30% of 20% of probability B will inference A. Something that's binary. So each entry is a binary distribution. And we're interested in approximating the posterior, that is, the probability distribution of A given that sequence or given the data set S. And we can do this by a variational inference.
How is it a binary matrix if it's if the IJ are probabilities?
So it's a binary. So each entry is a binary random variable. It's a Bernoulli random variable. So you can think of each entry is 0 and 1. But with probability,
it's you're saying it's a randomly chosen 0 or 1 at each entry.
Right, it's a distribution. So each entry is a binary distribution, a Bernoulli distribution. So that means there's probability, P, that event J would inference event I, right? Then.
Okay, I think I understand what you're saying.
So flip a coin, right? So you can think of
right.
the distribution. There's a parameter P that governs.
That governs what that is, what that element is.
Right,
Okay.
right. So yeah, P equals 70. Maybe you flip it, 10 times, roughly 7 times will be on the side that will be interest, right? So
And each of those IJ have a different probability distribution.
right. Each AIJ is binary, but the parameter will be different.
Okay, got it.
So yeah, and then through variational inference, we can we first, for convenience, we assume the prior is it only contains decoupled term. That means each entry of that probability distribution is not affected or is independent from other entries, right? And then we can calculate the evidence lower bound, which the first term is intuitively, this is saying I don't want my posterior or approximate posterior to be too far away from my prior, what I prior thought. But I want it to be faithful. The second term say, I want it to be faithful to my data. That means I need to fit my data fairly well. So it's a tug of war, right? So I don't want to be far away from my prior belief, but I want to be faithful to my data. I need to fit the data well. So this is the evidence lower bound. So yeah, the key is really how the encoder part is to convert attention to inference. The attention scores are essentially the softmax dot product attention score. That means how each instance, in event instance J, how do I need to attend to my past instance I? So if I have a sequence of length L, right, then my attention score will be L by L. Think about that. That means my event J, for each of event J, I need to, to pay attention to my past event, right? So that gives me about L by L. But we cover it so that it's only lower. Yeah, this will be lower, straight lower triangular, so that only the future events attends to the past event, but not vice versa. And then to make it to really inference, so we have to convert. So S, the attention score S inc, right, is L by L. Then we need to convert it to be by number of types by number of types, right? We need to summarize how each type-wise J attends to past event I, right? And then we use this P matrix that is essentially for each row is one hard encoded event. So each row indicates what was the event type that occurred on that row. So P is number of type times by L. So in this way, you can convert it. You can sort of summarize it from instance-wise to type-wise. And then the probability, then we use the sigmoid projection to make a proper probability distribution. And decoder is from inference to using inference-aware attention. So the goal is I need to make sure that once I sample this event, matrix A here, I can show this, yeah. From my approximate posterior, I need to tell my transformer in the tension mechanism that, hey, if this is not apparent, then I don't need to pay attention to that, right? If that does not inference, if event J does not inference I, then my future events of of I should not pay attention to J. So that's all it about. So, and again, we simulate the synthetic data with the Hawks EXP and proximal graphical event models, and this seems like we perform pretty good. Here, our model is IA-MTPP uniform and sparse. The uniform is my prior PAIJ for each of the element or each of the entry. I have 0.5 probability that J influence I, and sparse is a 0.2, 20% of probability. Yeah, we can see that overall they perform relatively well, although there's one good baseline cost model that perform very well on the MHP.
Could you just describe a little bit about the diabetes data set? I mean, what is it?
Oh, very good, very good. Thanks, Dr. Morgan. So the diabetes data set is a patient level data. There's a 70 or I believe 70 patient data where they keep track, for over a year, what are the possible events for these patients during, daily events. These events include taking a meal, right, exercise, and then blood pressure. Does the blood pressure change, increase or decrease, right?
Insulin injections, things like that.
Right, insulin injection. So yeah, in this case,
There's lots of types of events.
right.
Non-uniformly across time for 70 patients.
Right. The patient actually record their events, So yeah, and in this case, our model with the IATBP also is performs the best to classify the potential structure, right? Yeah, overall improvement with respect to F1 score. Of course, this can be improved with the accuracy. But efficiency wise, if we just use our model using a transformer type of attention, this is much faster compared to message passing algorithm that people used previous, the NRI-TPP. In dimension, 100, 200, 300, 400. That means there are 100 event types, 200 event types, 300 event types, 400 event types, right? You can go very high dimension. So, and then this is much faster. This is the time for completing the run, and on the left side is the accuracy. So yeah, in summaries, we beat the other model, the baseline, by performing much faster and then improved accuracy.
But those are type predictions, right?
Type. So the structural.
Oh, okay. Right.
So that means if we have some sort of a graph, right, I can, I need to infer the graph type or the.
Right. I get it. Yeah. The time doesn't apply in this case. Yeah.
Right. And sometimes the event sequences come without timestamps. Because not accessible, right? Because in healthcare data, these data could be aggregated by months. The insurance data, right? They aggregate by months. And then the prior event type really impact the occurrence of later high-cost patients. And then in software, there are error logs or execution traces, they may not have a time associated. So yeah, really identify this will affect critical events, such as failures or web-based attacks. And in NLP, natural language processing, when we're trying to extract data, that we not always can get the time right associated if we're trying to extract textual data. So yeah, you will see then the sequence will just with labels, right? Just with label CDA. And then, yeah, there are 5 types of events for this, like A is medication refill, B is cardiac event, C is emergency visit, D is hypertension diagnosis, E is anxiety diagnosis. And you will see that maybe some underlying graph that generates this data, right? So
when you say that C is of interest, then what you're trying to do is to predict when the next C event will occur based on what?
in this case, yes, that's one thing. That's one thing. We'll predict when it will be next event of C will happen, right? And
Yeah. So you could, there's several different ways you could do this then. You could say, well, regardless of type, what's the next event that's most likely to happen?
right,
A, B, C, or D.
right,
Or you could say, what is the probability of another C happening in a certain period of time?
that's right. Yeah, these are what you say is a hitting time, right? We're interested in C when that arrive. Yeah, so the time arrive. Now here we're interested in more of the structure or which are the events that influence C that has an impact on C on the arrival of C, right? Here will be directly will be AB, right? So and we can actually do this with a slight change of our model, previous model. So this is our probabilistic attention to inference neural models by changing the likelihood term and modifying a little bit on the posterior term, right? So we can change, and then still this will aggregate meaningfully instant-wise to study the type-wise inference, and then that will still capture the long-range historical inferences and the potential dependencies that involve nonlinear interactions. Okay, this is the last part. Causal inference example. So yeah, causal inference, we should be fairly familiar with this topic. So so we have a group of people, maybe there are some of people are taking this drug, the other is not, or the other group is not. So and there are different outcomes. Maybe one in this group, there's more people, their blood pressures increased or decreased, right? And then this group will have different outcomes, right? So causal inferencing observational data usually involve the covariates, treatment, and outcomes, right? And usually people have some theoretical framework, which is called the potential outcome frameworks. In the binary case, each unit I with covariate xi either receive treatment or control. That is, the treatment will be ti equals either 0 or 1, right? And then the potential outcome will be yi for that unit I, either they will either receive or not receive. So they can only, there's only one of them will be the factual, the other will be counterfactual, right? The counterfactual means that what if that unit I took that medicine, but in fact he or she did not. So yeah, there's a couple of assumptions. It's stable, and then it's consistent, and then positivity, and meaning that each unit has a chance to receive the treatment. And then ignorability, meaning that there's no unobserved confounding that will affect my assignment. And treatment effects can be defined at a population and treatment group. So we have the population level. This will be the ATE, which is the expected difference of outcome between the two groups. And then you can be conditioned on the treatment groups, so that my only interest will be in the treatment group, right? In this case, in a lot of health evaluation studies, ATT is more relevant to policymakers. They can be estimated through the sample mean. Yeah, matching and weighting. The key idea is we want to compare people or units in different treatment group, but they need to have same or similar covariance, similar characteristics, right? So match. Matching is a similarity of a covariance. Maybe you can match in the raw space, you can match in the propensity score space. Matching the raw space, meaning that for treatments and the control, they need to have similar age. You can think of that. But once you have more characteristics, more features, it's hard to compare, right? How similar in high dimensions. Now they use the propensity score, is how likely they get it treated. If they are for control and for treatment, they are equal likely treated, then we can look at their outcome, right? The difference will be a very good estimate of the effect. And balancing score is essentially any function that can map deterministically to the propensity score is called a balancing score. And you can see there's also weighting so that usually called inverse propensity score. These are also for adjusting for the covariance. Yeah, the goal is to make sure my two populations are similar or are very close to each other, right? Then we can draw any conclusion about the treatment. So treatment effect continuous time. For multivariate temporal sequences, they can be considered RID sequences. And the question is how would one event in history will impact another in the future? Examples for a cause event and effect event, where we just discussed meals or insulin intake and exercise and blood glucose level change of a diabetic patient. Maybe you're interested in exercise. How I do exercise at one point will lower my blood glucose level, for example. This will be interesting. And there's other examples here. Here is more illustrative one is through this graph. So we have a sequence of events, right? There's 3 types: prescription refill, hospital admission, home house visit, and then for that patient, for that person, there are events happening in the continuous time. But then we can know if we have discovered that graph. If we have that graph here, then maybe we'll be interested in how prescription refill would affect my hospital admission, the rate of hospital admission. Maybe if I constantly refill this, taking pills, that will reduce my rate to be admitted to hospital. So yeah, there's no such work has been proposed. So propose this causal inference framework for point processes. So we're interested in a parallel event, the Z and Y, which I just mentioned, will be prescription refill and hospital admission. So we can define the treatment variable ZT at time T. So this will be as a function of historical prescription refill. And then if we just use the recent history formulation, that means at certain point where we're interested, we can look at a window, maybe a week, looking at that window a week to see if there is a prescription refill occurred in that window. If there is, then we say yes. Then at this point, this will be treatment equals to 1, right? It's a treatment group. And if it's no, then this will be no treatment. And outcome, we can really looking at what's my future hospital admission rate, right? If also with there's no window. So yeah, we can look at the rate. If I taking that medicine, that is like within the week window, right? In the week window, if my rate decreases, then we can quantify the effect, right? And then we have to adjust the covariates. So we define the covariate at time t are using the recent history formulation, that if I observe in that window, if that covariate event occurs, then I say this is a 1. If it's not, then this is 0. So this is also used for us to make sure that when we do when we draw a causal conclusion, we need to make sure the covariates need to match.
You've got like 3 minutes.
Okay. So yeah, as a measure of causal relation, so we can define this ATE, right? This ATE is essentially saying, for the treatment group 1, right? And for non-treatment group, what's my rate of decrease for hospital admission? And then I take the expectation on average, how much that decrease. And then we can adjust by, again, using the propensity scores here. And then we have to estimate this AT in practice, and then we need to learn all of these parameters, such as the window and also the propensity score. And in order to get the propensity score, we need to actually access the duration of how that covariate will happen, and also the rate of the outcome given a parent state Z, to get the lambda 1 and lambda 0. And this can be computed through inverse probability treatment weighting. So yeah, with the PGM learning, so PGM is piecewise constant conditional intensity, I was just showed. To learn the model, we need to learn a graph, a set of windows and conditional intensity, a set of conditional intensity for each node given its parent. So, and the graph and the window are NP hard. So learning this is really through search and heuristically. But the parameters given the graph and also the window has closed form, so we can get it nicely. And here are some experiment evaluation that we've done in the past. yeah, using our approach that is here specified IP stable that results the minimum or the lowest root mean square error, which is you can see that's the peak line here. So it's consistent improving upon the other models. This is my last project that I'm working on. So consider the case when there's no timestamp, right? How can we quantify this? Again, I propose some definitions here, which is you can see will be different from the continuous the case with timestamps. But because of time, we will just go through quickly. So yeah, one of the interesting aspects is if we're trying to use a transformer type of architecture, we can arrive very nicely that a transformer G will generate a full spectrum of balancing scores at each instance I. I is the for time event instance I, yeah, and also a sequence of balancing scores. So yeah, I'm working on more of the theory and computation. So that's pretty much it. Yeah. So I'll be interested in doing the future work in latent variable models on point process and neurosymbolic and trustworthy point process, and then sequential decision making, continuous time, and causal reasoning can be applied in genomic and biological sequences. That's related to disease. Yeah, I'd like to thank Professor Christian Bennett as my advisor and the IBM team, and then the RC directed by Dr. Heller and my CISA committee members, Professor Yang and Professor Kramer. So, and then I thank everyone for listening. Thank you.
I'm going to stop the recording. So